portrait of Alan. So now, last but not least, for sure, it's a pleasure to welcome George Doschek. Can you hear us? Are you ready,
yes,
George?
Can you hear me?
Yes.
Yes, I'm going to. Can you hear me?
Yes, yes. Yes.
Can you hear me all right? I'm going to send my presentation over. There it is. Well, thank you. It's a pleasure to be in Paris in June. Well, sort of being in Paris. At least I'm not jet lagged. I first encountered Alan Gabriel when he was working on the satellite lines of X-ray spectra, which you just heard from Brian, and earlier I think from Ken Phillips. And this is how I got involved actually in solar physics, and Alan Gabriel's work was very seminal in this regard. Basically because he explained the appearance in the X-ray spectra of, well, actually an infinity of lines due to dielectronic recombination. And he explained the difference between the lines that are formed by dielectronic recombination electron impact excitation, and this enabled us to understand some of the spectra that we had at the time. There were several papers published, but the key paper wound up being published in 1972, and as of a few days ago it had 529 citations, which is a lot of citations, and it shows the value of this work. The X-ray spectrum of the sun is really important in solar flares and trying to understand solar flares. And what I have here, I don't know if you can see my cursor or not, this is what's called the standard model of solar flares. And in this model, magnetic reconnection occurs in a current sheet up high in the corona, which accelerates particles and also heats gas, causing conduction fronts and accelerated particles to go down into the chromosphere. And this heats the chromosphere, and multi-million degree plasma is bubbled up into closed flux tubes. The loops get closed after the reconnection occurs. Many things are believed to occur in this reconnection region, which is actually dark and not very visible. But the X-ray emission in the closed loops is bright, and that's what makes soft X-ray solar flares and produces the soft X-ray flare spectrum. Now over here are just some models of what happens in the reconnection region. Some people think there are magnetic islands formed. In here, their particles are accelerated in this particular model by a Fermi acceleration, et cetera, et cetera. The temperatures get very high. The temperatures get like 40 to 100 million degrees in this region, and only in the X-ray region can you see spectral lines formed at those temperatures. So here's another example with the RESI satellite. People have seen the high-energy X-rays appearing in flares before any other sign is seen in the chromosphere of a flare. So the X-ray region is really important. When I started, we had data at NRL from the sixth orbiting solar observatory satellite, OSO-6, and the resolution of the spectra was very, very poor. In this top panel on the left, you see a blob, which is due to iron emission lines. And in the bottom, you see lines, the triplet that Brian mentioned of helium-like, potassium here and calcium over here. Here's a blow-up on the right of some of that data. The top two panels on the right show the iron and the calcium data. And we wondered what these lines were, and it's due to Alan's work that these lines were actually identified and grouped together. And you can see in the spectrum of calcium on the top right that I have some of Alan's lines there. Similar work was also done in Russia by Weinstein, but it was Alan that published this paper and grouped the lines and gave them various letter designation names. Now, as Brian also mentioned, along came the Solar Maximum mission in the early 1980s, and Alan was one of the principal investigators of that mission. There were three PIs. There was Len Culhane at Mullard, there was Alan Gabriel at Rutherford, and Lauren Acton in the United States. Keith Strong, a student of Len Culhane, actually made up an acronym for the three PIs called Actanial. At any rate, at that time at NRL, we were competing with the SMM program. We flew Bragg spectrometers on Department of Defense P-78 spacecrafts, P-78-1. But you can see the spectra that we got from P-78, they look very similar to what was gotten from SMM. and also the Japanese with the Hinode mission, which was also flown at about the same time. And you can see that many of these satellite, this blob that we saw on the top resolves into all these satellite lines. Now, the satellite lines are important. What Alan did, the first thing he did that was really nice was he named them all. He gave them letter designations so that if somebody at a party asks you what line you're working on, you don't have to say, well, I'm working on a 1s squared 2p double t 3 halves or 1s 2s squared double s a half line. You can just say I'm working on line O. So this made it very nice. And some of these lines are formed by dielectronic recombination, and others are formed by intershell excitation. And this allows for a temperature diagnostic in flares that's independent of ionization equilibrium. Here's the line ratio 1 here, and this depends on the actual theory that's being used. It was being refined in those days. There were several curves here. But basically, you can see that the line ratio is J over W. W is the resonance line of helium-like iron, and W is the resonance line here of helium-like calcium. And J and K are dielectronic recombination lines, and it's very sensitive to the temperature. The TEM here is the temperature of maximum emitting efficiency and ionization balance for iron and calcium. And you can see there's a very strong temperature dependence. We used the results from Alan's paper to compute temperatures in flares. These are light curves of solar flares obtained with our spectrometer of iron 25, calcium 19, and calcium 20. And by looking at the ratios of J over W, we were able to compute the temperature as functions of time in the flare, as you can see going on like this. So we were eventually, when the Yoko satellite was flown, and we had Bragg spectrometers on Yoko in 1991, we were able to take the GOES classifications of flares, X, A, B, and C, and assign temperature groupings to them based on the analysis of the X-ray flare spectra. To show you dramatically what a spectrum of iron looks like for different temperatures, here's, this I think is actually a synthetic spectrum that we made. There's a dashed line is 12.6 million degrees, and the solid line is 20 million degrees normalized to the resonance line of iron 25. You can see there's a huge difference here. So this enabled us really to understand what the maximum temperatures in the soft X-ray region are in flares, and they actually don't get much greater than about 23 million degrees unless you have a super hot component, and then they can go up to 40 million degrees. Now there's another aspect to these spectra that's interesting, and that's that if you look at the resonance line of, in this case, calcium, and you look at, this is a resonance line on a log plot, there's sometimes, during the rise phase of flares, a blue wing of the line. And this is the chromospheric evaporation that I mentioned in the theoretical slide earlier. And we could see this, but unfortunately all the spectrometers at that time had no real good spatial resolution. So basically we're looking at the spectra of the entire flare. So there are foot point regions that produce this evaporation, and then there's other parts where the gas stops moving and produces a stationary component. And all the spectra we saw always had a stationary and blue shifted component together. And also at the same time, if you look at the line widths of the resonance line, we found they were very, very broad during the onset of flares, and you get temperatures and turbulence of 130 kilometers a second. It settles down a little later to 80 and 60 kilometers as you reach the peak intensity of a flare. So these dynamical things also showed up in the spectrum. So what I'd now like to do is switch to the future, what's actually happening in this line of research. Tragically, the X-ray, the resolution of the X-ray spectra, the high X-ray spectra sort of ceased after the Yoko mission in '91. However, we can still do work on highly ionized iron in the EUV with using multi-layer optics because we see lines of iron 24 and 23. These are due to transitions within the ground configuration of the ion. So I'm going to switch now to results from EIS, which is the extreme ultraviolet spectrometer on the Hinode satellite. And the image that you see in the inset here is an image of a flare in the spectral line of iron 23 at 263 angstroms. And it looks like many flare images, mainly like scrambled eggs, like an English breakfast. And I've marked on here several spots that you can see. There are 5 of them. And on the right, I'm showing the profile of iron-23 that we got from each location. Now, in the case of the histogram spectrum, you see both a blue shifted and stationary component like we saw with BCS, SMN, and Yoko. But now on some of these other spots, like this one over here, there is a completely shifted component. This is the site of one of the evaporation foot points in the loops. And it's by studying such things now that we can actually begin to try to check details of the standard model of solar flares. In this case, the shift of this line from the center is 150 kilometers a second. And this is similar to what we got often from Yoko and other satellites. Here's the same image, and here I've plotted a path through the image. And down here, I'm showing the upflow velocities from iron-23, and as comparison, since I sees cold lines as well, I'm showing coronal lines of iron-14 and iron-16. Now, the models that people have made with 1D models of evaporation show that the highest speeds should come from lines like iron-23, 24, and 25. And then as you go to the lower speeds, the speeds actually slow down and can actually become a downflow because you get a momentum recoil. When you heat the top layer of the chromosphere, throws the gas up, and then the colder stuff gets sort of pushed down or doesn't come up as fast. And that's exactly what we're seeing in this particular plot here. So now, with ICE, there's a lot of work going on, looking at flares, looking at the images we get, especially from SDO when they're not saturated, and trying to see the foot points of these loops and check models of chromospheric evaporation. So that's going on in the future. Now let me go back for a moment. Here, these are X pixels and these are Y pixels. Suppose I just take a look along Y and just plot the upflow speed along the direction of the Y-axis here. Then I get plots like this. For a given here's one X pixel, another X pixel, and here's the plot as you go on Y. And so you can actually locate these downflow regions and also upflow regions and also the downflow regions that you get. And the downflow can come also from an evaporating foot point. It's just where the material is compressed. And for pixel 19 here, I have at this point right here the profile of iron-23, and you see it's totally shifted at this point. So these studies are ongoing now with ICE, and they're a continuation of work that was started back in the 70s where Alan played a key role. So what do we need now? What I would like to have, if I could have all the money in the world, is to actually fly a much more sensitive grouping of Bragg spectrometers that look not only at iron-25 in satellites, but also the iron-26 satellites near 1.8 angstroms in the reconnection region. Iron-26 being hydrogen-like iron. Hydrogen-like iron also has satellites. You can arrange these spectrometers such that you can also measure polarization. So if the particles, the electrons in the reconnection region are preferentially accelerated in a certain direction, you can measure that. Because later on, Jacques Debeau and a group of us at NRO actually measured polarization of X-ray satellite lines using the Livermore EBIT, electron beam ion trap. So another thing you might do is use microcalorimeters as they would be developed for flares, but right now they're not really too good for flares, but maybe in 10 years you can use microcalorimeters, and this would give you imaging as well as high-resolution spectroscopy. We also need higher and more sensitive types of instruments like ICE, like the Solar Sea instrument that the Japanese are planning. And in fact, we're doing this. Luca Teriyaka is leading a group that's developing a really high resolution EUV spectrometer that would be flown on the Solar Sea mission. And we need also advanced hard X-ray imaging instruments like RESI. At any rate, Alan Gabriel was a key individual in the ground floor investigation of the high temperature components of solar flares. And understanding flares is a real cosmic adventure, and I hope we can all continue to try to unlock the secrets of the sun in the future. Thank you.
Thanks a lot, George. Is there any comment? Oh, yes, Alan.
I really want to take this opportunity to thank George for coming to this meeting as he has, and appreciate the contribution Unfortunately, I can't thank him personally after the meeting because the screen will go off and I'll lose him. Can you hear me, George?
Yes.
Oh, okay. Thank you very much.
Sorry, I can.
Yeah. Okay. I don't know if you got.
Well,
Any
it's
last
a
question?
pleasure to be here. I'm sorry I won't be able to share in the festivities to follow.
Okay, so as we are very, very late, so I will like to thank again all the speakers of today and to thank the laboratory of linear accelerator, the laboratoire d'accélérateur linéaire, who allowed us to have a nice place to be, to share this day. Thank you again, Sozolal Laboratory. Thank you again, George. Thank you again, all of you.
Hey.
And we have to move fast to the main building of EIS, where we are waited. So take all your stuff with yourself. Let's go. Exposition magique.